Hello to everybody, welcome to this video. Today I would like to show you how to do Earth contact between spheres with Abaqus. To do so, the model we are going to use is just two hemispheres in contact by the internal face of the big one. So it doesn't matter if it is a hemisphere or a sphere, the important thing is the point of contact. So if we cut the cuts by 2, we can see this is the sphere, small one, this is the big one. And to do this modeling, I will use Axi-symmetric model of this. So in which the axis of symmetry is this one, and the radius of the geometry and dimensions of the first hemisphere will be these ones, and the radius of the second hemisphere is this one. The material will be steel for both hemispheres. Abaqus units will be Newton millimeters, tones, and seconds, also kelvins, but we are not going to use any temperature. The loading will be a vertical load applied on this node of 500 newtons, and the target will be to get the radius of contact area. The contact area will be a circle, so we need to check to get the radius of that, the maximum pressure at contact, and the normal and shear stresses. So this is a good exercise as we can check against analytical formulas. There are analytical formulas to get all of these parameters, and these ones are shown in the following slide. So we get all the results with Excel spreadsheet, and we got all this. This is the contact radius, maximum pressure, stresses. Okay, so what we are going to do now is just go to Abaqus and get the same results to check if are very similar or not. Let's see. So here in Abaqus, what we need to do first is just check the set working directory. So let's start creating a part. As our model will be Axi-symmetric, I need to click on here, change the name, hemisphere 1, deformable will be shell, yeah, continue. So we're going to create the first point. Here I'm going to click the coordinates, 0, 0, I have this point here. So as the radius will be 160, so I will create 0. So the dot, sorry, you can see it. Oh, sorry, because it's not created. Okay, there it is. Always out of this pattern is okay. So yeah, I will create 0,160. Sorry, negative 0, minus 60. Okay, so I will create an arc. Click in the center, this, okay. So now I'm going to create the internal radius. So again, the radius will be 160 minus 10, so the radius will be 150, so it will be here. Oh, sorry, 0, minus 150. Okay, so again the arc, close the sketch. Okay, so this is the Axi-symmetric model. Okay, and now I'm going to create the internal sphere. So create hemisphere 2. Continue. Okay, so again 0, 0. The radius will be 60, so 0, 60 is here. 60, 60. Okay, so now I can create the radius, the arc, and now we'll close the geometry. So yeah, we have two components. So what I need to do now is just go to property and define the material property. It will be steel, only elastic material properties needed. So yeah, gigapascals, and Poisson ratio 0.3. Okay, so now we need solid homogeneous section. Continue. Steel, yeah, great. And now we need to assign the section to every component from section. Okay, and now select do the same for the hemisphere 2. And okay, so okay, that's applied. So next thing we need to do is just go to assembly, create assembly, hemispheres, make independent. So okay, now we need to translate this instance from this point to that point. Okay, so looks good to me. So let's move on to step. So we need to create the step. It's gonna be static general, okay, with nonlinear geometry on 0.1 initial step. Okay, so we need to create interactions. So first thing we need to do is just create an interaction which is going to help us applying the force. So just coupling, click on this, okay, surface, the top, okay, constraint degrees of freedom, all of them, yeah, kinematic, okay. So we are going to apply a force here, and all the nodes on this face will have the same behavior as this one. So although the force is applied on this. Okay, so next thing we need to create an interaction, contact. So tangential behavior without any friction, fine. And the normal behavior as it is, hard, contact, default, okay. So next thing, I would like to go to load and apply the load and boundary conditions. So first thing will be the load, will be a concentrated force, apply on this point, okay, and will be y direction will be minus 500, okay, okay. We can see it there. So now we are going to create the boundary conditions. The boundary conditions will be encaster this edge. We need to apply axisymmetric boundary conditions on these edges, and we will restrain the x motion of this sphere, hemisphere, apply boundary conditions on this top edge. So first of all, yeah, go to step, encaster, symmetry, anti-symmetry, encaster. We select this edge, okay, done. Select encaster. We'll remove all the degrees of freedom of this edge. So next will be Axi-symmetry. symmetry. Okay, and will be this shift, press shift and click on this edge. We have selected both, done, and now select Axi-symmetry. Okay, and the last one, symmetry. Well, in this case we displacement rotation, we call it top, continue, select the top edge, done. So here we can select U1, direction X direction, and rotations in Z. Okay. So yeah, I think all the loadeds and boundary conditions are applied, so let's move on the mesh module. Okay, here we need to create some partition in the model. So we will partition face and click on that. Okay, so we expect higher tension on the first millimeters, so the mesh will be much smaller within the contact region, near to the contact region. So I will create here what I think I'm going to do, yeah, I create a line. This will be 1 millimeter, 1, okay, and I will create another one. This will be 5. So, oh, sorry, within the 5 first millimeters the mesh will be finer. So I will create now an arc from here to there. Sorry, I'm doing wrong, because what I want is just the opposite, from here to there. Okay, another one from here to this point. Okay, and now we can do it. Okay, so the partition is done. And now we do the same with the bigger hemisphere. Done. And we do exactly the same. Just click on here. This will be 1 millimeter. And click another one. Okay, so 1. Okay, and this one will be 5. Okay, so let's create the arc. And the same with this. Doesn't matter where it finishes, just there. Done. Sorry, so something wrong I've done, so I'm going to delete this and this. Done. So I think it matters where this arc finishes, so just go there, this go there. Okay, yeah, so yes, definitely it matters where this arc finishes, ends. So yeah, so I need now to go to select the element types. Done. So will be Axisymmetric with stress, linear, yeah, should be fine. We assign mesh control, so free will be quad is okay, medial axis, select medial axis, okay. And now we need to check the global sheets, so all the parts. Global sheets will be 1.5, well, I think 2. Apply, yeah, enough. And now we'll select the local seeds. So to do that, we'll select all these edges, just holding Shift. So probably I need to go, okay. So I'll select it, done. Well, sorry, no. I need to first select these ones because sizes, local sizes will be different. So first I need to select these ones, done, by size of 0.01, apply, okay. Now the next one, okay, done, and this will be 0.1, apply, okay. And now we can mesh whole components. Okay. So as we see here, we have a really fine mesh, a bit thicker here, and much thicker here, far from the contact. So yeah, looks fine to me. So what I need to do now is just quickly go to Job, Manager, create a new job from Model, Contact, semihespheres, continue, okay, can use multiple processors, it's fine, and we can submit it. So I will pause the video and I will show you the results when it's completed. So the model is completed, but I forgot to create the interaction. So the model has converged, but there is no contact between them. So I need to create, we created the interaction, but we didn't create the contact pair. So just quickly go to contact pair and select the surfaces. So the master slave will be, the master surface will be this. Just click Shift and select all the three edges, done. And the slave type will be geometry, and the same, select these three. Okay, done. So here we need to click on small sliding node to surface and select the interaction property we want, and that's fine. Okay, so now it's created. So let's go back to Job and just click on Submit again. Okay, and I will do the same, just pause the video and show you the results after. The job has completed, so we can click on Results. We can visualize the results. First thing I'm gonna do, if you see the mesh, you can check it by applying exterior feature edges, okay? And what I need to do now is just sweep the elements, sweep extrude. Okay, so we can see this cut. Okay. So I think it's all. So what I want to do now is just quickly go to see the stress. Like this stress in X direction. If you can see the minimum and maximum, you can go to here and click on Show Limits, Show Location, minimum and maximum. I think we need to see both, it's fine. So we need to go quickly zoom in. This is the contact, stresses of the contact. So the maximum, the minimum in this case, because or the maximum compressive stress is this one, 408.5, so we can go here. .5. Can say it's negative, so this is very close to this value, so looks fine. And y stress in y direction will be this one, 525.3. So we can again very close to the analytical stress. Let's check the shear stress. Shear stress, if we go to shear stress here, this one, this is not going to show us the real stress. We need to create field output. Just quickly going to field output, create from fields. In the description I'm going to leave the link to a video I did showing how to operate with this and manipulate all these field outputs. So shear, I will call it. So we need to go to scalars, go to shear stress will be this, maximum minus minimum divided by 2. So we select stress maximum minus stress minimum. Okay, so now we need to go to here, session step. Okay, apply. And this is the shear stress. So the maximum shear stress is 156, but it's not at the contact point. So we'll go zoom in and let's go to tools, query, node, proof values. So here we need to select nodes and select shear stress will be 56.1. So quickly go to PowerPoint, 56.1. So again, very close to the analytical value. And now we'll get the maximum pressure and the radius of the contact area. So first we need to close this, quickly change the step, go back to step 1, represent C press. Okay, I'm going to remove the outer hemisphere. So here we can manipulate the part instances, remove. Okay, so now we only have the outer. Well, I would like the inner, to be honest. Okay, that's there. So to get the contact path, the contact pressure, we need to create a path from node list. This one, as before. Okay, so at the beginning we can select every 3 nodes, because if we have a lot of nodes, it can take quite a while. So now we can select every node. So we can select a few more. Should be enough. Click on done. Okay. So we can delete this because it looks like there is an error there. Okay. And now we go to XY data, click on path, continue, select our path and plot the results. Okay, so I think we need to select a few more nodes as this value of the pressure is not 0. So let's go to the path. Sorry, go to here, path, here, add after. Okay, should be enough. Okay. So XY data, path 1. Okay, cool. So here we have the value. To check when this value is 0, we can go to XY data, click on this and right click and plot. No, sorry, edit. When x is 0, sorry, when y is 0, we have, this is our radius of the contact area. So Control C, sorry. Go to PowerPoint and check. So what looks very close to the real value, analytical value. So it's fine. And the maximum pressure, we'll get the maximum pressure from the, we can get it from here, but we can plot it, C-press, and check the maximum value. It is 530 megapascals. So yeah, the results are very close. So this is a sign that we have done a very good job here. So yeah, I think that's all. Thank you very much for watching this video. Please don't forget to subscribe to the channel and like us. So thank you very much. See you later.